try to
Okay, let's get started with the morning talk, which is at 11 this week. And we have Joost who will talk about topological Bose condensation and fractional quantum Hall hierarchies.
Okay. Well, thank you for coming, and of course thanks to the organizers for organizing this wonderful program. We've really been enjoying it, and I hope you all have as well. I'd also like to say that you were all very lucky that I'm here, because I wasn't really sure whether it was half 10 or 11 this morning. I arrived after half 10. So. Anyway, so topological Bose condensation and fractional quantum Hall hierarchies. So this is mostly based on work that I've been doing with my former PhD supervisors on the RISE and with his student Shanna Haker. There will be a bit of mention of work that is in preparation with Parser Wonderson as well. And really this is about the kind of program that we've had going on ever since at least 2002, and also with Bernd Schurz at the time, to try and understand transitions between topological phases. And we started from a sort of rather abstract point of view, which I will start to explain. So recently we've been able to extend the framework far enough to actually make some contact with real physics, like fractional quantum Hall hierarchy states. I'll tell you some of that in the latter part of the talk. Now, before I go on, I should mention my sponsors, which are of course my affiliations, and the Dublin Institute for Advanced Studies, and more importantly to mention the Science Foundation of Ireland. So what is this Bose condensation or topological symmetry breaking? So the idea is, like I said, we want to study transitions between topological phases, and there's a problem immediately, which is that we don't really have a guiding principle there. So if we study transitions between ordinary phases, usually there's some symmetry that's broken, and then you can use the symmetry breaking as your guiding principle in finding the excitations of the new phase and explaining what happens. But here, topological phases, you don't actually have to have a symmetry to have, or a local symmetry to have topological order. Unfortunately, it has become clear, probably to some people already in the 1980s, but to most of us probably more recently, that you can actually describe systems in topological phases by some generalized symmetry principles. So for example, you could have some tensor category or topological field theory or Hopf algebra or quantum group, all of these more or less equivalent, that describe the spectrum and the interactions of your topological particles in your theory. So more concretely, let's think about it in terms of a quantum group. So a quantum group is some kind of algebra which acts on the Hilbert space of the theory, and the different particle types of the theory should be in a one-to-one correspondence with the irreducible representations of this quantum group. So this is analogous to what happens when you have an ordinary symmetry describing your theory. For example, if you have a SU2 symmetry, then you have spin particles of different spins, and the different spins are different irreducible representations of this SU2. If you want to describe addition of spin, then you have to think about the tensor product of these different SU2 representations and do Clebsch-Gordon decomposition, tensor product decomposition. So the idea is that this fusion in the arbitrary topological theories should also be able to describe that with tensor product of quantum group representations that correspond to different particle types. And then you can do various other things. So you can have grading of the particles, and you can have twist of the particles, or topological spin. And those are all described by various structures that come with these quantum groups. So the idea that we had was that you should be able to do something which we would call topological symmetry breaking, or basically you should be able to do all the steps that you usually do in studying symmetry breaking phase transition, but using this quantum group symmetry instead of an ordinary symmetry. In order to make our task a bit more concrete or simple, we started with the idea that the mechanism for the symmetry breaking should be some kind of post-condensation. So, it should be, for example, analogous to what happens in the Higgs effect, where there's some field or some order parameter which breaks the symmetry, the underlying symmetry of the theory, and then you're left with the stabilizer group of the order parameter. Anyway, so here, this is all still very abstract. So let me first introduce some basic concepts of topological order that I will need in the rest of the talk, so I can make all this a bit more concrete. So, of course, I was talking about quantum groups and tensor categories and all that stuff, but basically the only thing I need in this talk, which I hope you're all reasonably familiar with, is, well, of course we need to have different types of particles labeled by, let's say, labels A, B, C, etc. So different topological types. And these particles are going to have fusion rules, so that if I combine particle A with particle B, I can get various particles C, and well, I might have multiplicities in ABC which are integers, and they basically tell me that if I look at my Commons matter system or any topological system with a particle of type A and a particle of type B in it, then I have a vector space of solutions which have overall charge C, which is of this dimension, which is a nice integer. So, in addition to that, we're going to have twist factors, which are basically just the two-dimensional spins of the particle. So if I twist the particle around, think of this as the world line of the particle. You have to, well, you can't really think of that as the world line of the particle, but you have to sort of stretch it out a little bit so that this time-like, well, this reversal in time goes away. Anyway, twist the particle around, you get some phase factor out of the wave function. So we call this phase factor the twist factor. And so one of the things that we're going to require of a boson in 2 dimensions is, of course, that it's going to have a trivial twist factor, trivial spin. And well, once you know the twist factors, then you also know most of the braiding. More precisely, you know the monodromy, because if you have a particle A and a particle B, and you know that they're in a fusion channel C, and then if you take A all the way around B, you can untwist this diagram at the cost of introducing twists in the individual lines, this kind of twist. And so you can actually show that you get this factor out, which is just a combination of the twist factors of the particles A, B, and C, which A, B, and C. So once you know twist factors, you really know the monodromy of the theory as well, where you take the particles all the way around each other. And one of the things that we of course need to require is that bosons also have trivial self-monodromy. So if I take 2 bosons and I take one all the way around the other, I should not get a non-trivial factor out. So that it's going to be another requirement on what we call a boson. The reason I had to talk about requirements for bosons is because in 2 dimensions it's not quite as obvious what a boson is. In 3 dimensions you can either say it has integer spin, or you can say it has trivial exchange statistics, and those things are related by the spin statistics theorem. But in 2 dimensions it's a bit more complicated, so you have to actually put both requirements simultaneously. Anyway, so what now are going to be the overall features of the scheme that we want to introduce? So, like I said, the only thing that we really want to know about the topological field theory at this point is the fusion and the spin factors, which also determine the monodromy. So before we do a Bose condensation, we can have a topological field theory or quantum group with basically just fusions and spins. And let's call that A. And then we want to describe the effects of the condensation in 2 steps, basically. So first of all, there's going to be branching of topological sectors. So that corresponds to a symmetry breaking. Usually if you break the symmetry group of a theory down to a smaller group, then the irreducible representations, which correspond to the particles, will fall apart into the representations of the smaller group. So similarly, we expect to have something like that here, except now we're talking about representations of a quantum group. Okay, so that gives us a whole new set of sectors that we're going to branch to, and these sectors are supposed to have their own fusion, because of course we still should be able to fuse the excitations of the new theory together, but we're not immediately going to require that they also have good spins, because we want to allow that some of the sectors in the new vacuum, the new sort of condensed state, would actually pull strings in the condensate, so they have a branch cut if you try to break one of the condensate particles around them, and that branch cut is locally destroying the condensate, so it makes a string. Okay, so I actually have a slide on the next slide is actually a picture of that. Oh no, I left it out. Anyway, so then secondly, we want to identify which of these sectors don't actually pull strings, so which of them are really like point-like particles, and there should be some subset of these sectors of this intermediate tensor category T. And in particular for this subset of really point-like particles in 2 dimensions, we want again that they should be, they should have a good grading, so they should be good, form a good topological field theory. So in particular we want to have spins for them again, and as a result also monitoring them. Okay, so, and then we need some properties of this whole scheme. So first property when we do this branching is that we require that commutes with fusion, so that there's a lot about that on the next slide. And the second thing is that, well, we need to decide when a particle is confined or not. And I'm going to say more about that a couple of slides later, but basically if the condensate is not interfering with the spin of the particle, then it won't be confined. And then it has good grading. And finally, you'd like to say that if you have this intermediate theory which describes particles which pull these strings, then of course the strings, because they locally destroy the condensate, will cost a certain amount of energy per length, per unit length. So you can't just make them arbitrarily long. So there are basically two ways that you can still have excitations like that. Either they're confined together, so if you have one, you have to have another one where the string ends, and the string can't get much longer than the highest energy scale that you want to put in. Or they have to be connected to the boundary of the sample, right? Because you can always make the string end on the outside, and then you can't make them go away from the boundary too far, because the string will become too long, the energy will be too high. So then you have to think of them as boundary excitations. So this theory T has kind of this dual roles, describing both confined and boundary excitations. And you can also think of interfaces now where you have the original phase described as quantum group A, then you have the condensed phase described by the point-like particles described as U, and then you have the interface where this T theory is active. So, just to make it slightly more concrete what I mean with branching. So, like I said, we want to introduce branchings for topological sectors. So just like with branchings for group representations, if we have a representation A, and we look at it as a representation of the subgroup of the original group. So for example, this could be an SU2 representation, and these could be just representations of the U1 that lies inside. Then it decomposes into representations of the smaller group with integer coefficients here. And we're just going to pose that the same thing happens for these sectors A, and with of course the underlying idea that we're restricting from a large quantum group to a small quantum group. And these are representations of this quantum group. Okay, now of course we want to require that the particle that's going to condense, the representation that corresponds to that, should branch to the vacuum representation, because in the new theory you shouldn't be able to see that there's such a particle there. There's an undetermined number of them. And we have a further requirement. Of course, the new labels, we haven't determined what they are yet. The new labels should have good fusion rules of their own. So that means that the fusion rules of the new labels should be associative, and there should be a vacuum, of course, for the new theory and the charge conjugation, so with particles and antiparticles. But also, we want branching and fusion to commute, which is something that's automatic if you do this for groups. So if you just, basically it means that if you take the fusion of two particles A and B in the original theory, then you can choose whether you first take the fusion and then decompose the result, so restrict results to the smaller quantum group, or you first restrict the individual representations and then you fuse them together in the new theory using the new fusion. This is quite a powerful requirement actually, which we will see very soon. In particular, it implies that the quantum dimensions of the particles are preserved, which means just that if I have a particle of some quantum dimension here, then the sums of these quantum dimensions of these particles with the coefficients, with the integer multiplicities here, is equal to the quantum dimension on the left-hand side. But we don't put any requirements on the grading yet, because we still want to allow for confined excitations. Strings. Okay, so let's have a concrete example. So let's look at a theory where we have a symmetry which is basically Ising times Ising star. So if you think of the Leverman model for the Ising model, the double Ising model. So most of you have hopefully seen the Ising model before. So we have three types of particles, type 1, type epsilon, and type sigma. Quantum dimensions 1, 1, and square root 2, and the spins are given by these, let's do the logarithms of the spin factors. So, or we can think of them as the conformal weights if you want to think about conformal field theory. And if we do, and of course the fusion rules are here. So if we do Ising times Ising star, then the only difference between Ising and Ising star is that with Ising star we have the opposite spins. So the actual particles in this theory, there are 9 of them. They just have a label from the left and a label from the right. And the spins are, well, spin from the left, spin minus spin from the right, and the dimensions multiply. So for example, the spin of epsilon comma sigma would be, well, epsilon is spin 1/2, and sigma is spin 1/16, so you have 7/16. Okay. Now the first thing we can notice is that this theory has lots of bosons, because all the diagonal sectors here, x, x are of course bosonic, because they all have, well, first of all, spin 0, and then you have to, of course, check by hand, in principle, that they also have trivial monodromy, but really that means that if you fuse 2 of these things, then there's another boson in the fusion. But of course that happens because if you fuse 2 diagonal things, you always get diagonal things inside again. Okay, so we have lots of bosons in this case, actually 2 bosons, sigma, sigma, and epsilon, epsilon. So let's just look at the case where, suppose that the epsilon, epsilon is going to condense. That's the most interesting case in this case. So, okay, so epsilon, epsilon has quantum dimension 1, this 1 times 1. So it can only branch to a single sector of the new theory, because the quantum dimension is preserved and you can't take sectors with quantum dimension less than 1. And we already said that it has to branch to the vacuum, so in fact it can only branch to only the vacuum on the right hand side. Okay, now we said branching and fusion have to commute. So in particular that means that if I branch anything with the condensed particle, then, well, after I go to the new theory, that fusion doesn't do anything because the condensed particle has branched to the trivial particle. So basically in the old theory, any 2 particles which are related by fusion with the condensate just become identified in the new theory. So in this case 1 epsilon and epsilon 1 are related by fusion with this thing, so they're just identified in the new theory. So more precisely that means that these 2 things branch to the same field in the new theory, or they share the same sector from epsilon and subscript T. I'm not going to actually keep subscripts T, that's forgive. So now if we look a bit more carefully, then we see that actually all the fields here have quantum dimensions either 1, square root 2, or 2. And if they have dimension 1 or square root 2, then they can't actually split. Because, well, like I said, for 1 you can't make anything less than 1, and for square root 2 is the same thing. You can't split into 2 parts which are both larger than 1. So the only sector that can actually have a restriction with more than 1 part is sigma comma sigma, because that has quantum dimension 2. And so actually this has to happen because we use again the fact that branching and fusion are supposed to commute, then well, sigma times sigma gives you in the old fusion rules the sum of these 4 terms. Just because sigma times sigma gives 1 plus epsilon, and you get all the combinations. But we said that epsilon comma epsilon was going to be branching to 1 in the new theory, so that means in the new theory we have 2 1s, 2 trivial particles on the right hand side. And this is a property that we never actually want in the tensor category. We always want that 2 particles fused, there should be only 1 trivial particle on the right hand side. Now you might ask why, but basically if you had 2 different ways of making 2 particles, is there any? You had 2 different ways of making 2 particles then come together and disappear. Like this. Then you would also have to worry about processes like this, where you have a particle going along, nothing happens, but the vacuum is splitting off. Something which you couldn't actually see by looking at topological properties. And now this could happen in 2 different ways, because you could add like this, or like this, right, with these 2 different vertices. So basically, if something like this happens, the theory isn't really topological, because you have to have some other labels to keep track of what's happening. So, okay, so if we want that the theory we have at the end is still a good topological theory, then we better make sure that we have some other way of producing these 2 1s. And of course the obvious way is to split this sigma like it was on the previous slide, because then suddenly instead of having 1 term on the left hand side, now I have 4 terms. Sigma 1 times sigma 2, sigma 1 times sigma 1, sigma 2 times sigma 2, and sigma 2 times sigma 1. So clearly 2 of those terms can just be equal to 1, and then everything is fine. Okay, so in summary we end up with 6 T sectors, which are labeled by, well, just 1, which corresponds to both 1, 1, epsilon, epsilon, 1 epsilon, which corresponds to 1 epsilon and epsilon 1, sigma 1, sigma 1, sigma 2, which are the 2 parts of sigma sigma, and then it's again easy to see that these 2 have to branch to the same one, and these 2 have to branch to the same one, because these 2 are related again by fusion with epsilon, epsilon, in the same year. So these 6 particles. And then again you can derive the fusion rules of these sectors directly from the fusion rules of the original theory. Again by this assumption that it commutes, fusion commutes with restriction. So for example, the fields that correspond to 1, 1, 1 epsilon and 1 sigma, they just have Ising fusion rules, because in the original theory they had Ising fusion rules. And if you sort of look at it in a bit more detail, then you see that the overall fusion rules of this T theory with 6 particles actually the Ising theory times Z2. So, but I didn't give you any grading at this point. Oh yeah, I don't know how that's... Okay, so I guess this is where the slide was with the confined excitation. Anyway, so at this point we have a nice theory with some fusion, but we don't have grading yet. And the idea is that we don't necessarily expect to have grading at this point, because we didn't put in anywhere that you know the new vacuum has some coherence, and that we could have excitations from the original theory which don't fit in that, so that they make the order parameter of the vacuum have a branch cut and destroy the condensate along a line. So, okay, so we'd like to find out which of the particles don't do this. So which of these T sectors that we have are actually not confined. Well, if they're not confined, then the condensate shouldn't interfere with the spin or with the monodromy at all. So then we could probably require that a sector from the T theory is not confined if all the fields that branch to that sector, so all the original fields all the original sectors that correspond to that sector in the new theory have the same twist factor. Okay, so if you do this, then actually some nice consistency checks. So first of all, the non-confined particles, so the ones that satisfy this, they of course have well-defined monodromies with each other because they all have well-defined spin factors, and from the spin factors you get the monodromies. And secondly, the sectors which branch to unconfined particles, it turns out they actually do have trivial braiding with the condensed sector. So this is a good thing because it sort of confirms the intuition that the condensed sector is not interfered, or that you don't have such branch dots. And finally, of course, we want to have that the unconfined sectors, fusions and spins, or fusions and spins of those should be described by some topological field theory or some quantum group so that we can make everything fit together. I'm going to say on some later slide that actually now there's a mathematical theory which shows that you can prove that this happens. So it's a good thing. Okay, so but anyway, what does that mean in our case of Ising times Ising star? Here again we have the identifications between the various fields that branch to the same sector. Then if we look at the corresponding spin factors, then we see that, well, 1, 1, epsilon, epsilon, the condensed thing, they of course both have trivial spin. Just because we chose epsilon to be, we chose this condensate to be boson, so they're not confined, which is very good. It's actually a requirement from the start that this doesn't happen if they're confined. All the other particles with quantum dimension 1 have the property that, if there are two particles which branch to the same sector, then they have the same spin, so not confined. Or in the case of sigma sigma 1, sigma sigma 2, they actually only come from sigma sigma, so there's not even a chance that something will go wrong. But if I look at the particles of quantum dimension square root 2, sigma 1 and sigma psi, or 1 sigma and psi sigma, of course the difference here is actually this fermion psi. So actually they do have different spin factors, these two possibilities, and so the corresponding particle in the T theory will be confined, because you can't define a good spin factor for it to work with all of them.
First, a stupid question. Where did psi come from? I thought those were...
Oh, sorry, epsilon.
Oh, it's
Yeah. Epsilon and psi are the same
Right.
in Ising models.
That was the easy question.
Yeah.
So then another question, is this, keeping track of H mod 1, do I run into a problem that I really want to keep track of it mod a half for self-monodromy or something like that? I mean, is that
Yeah, that's a good question. So, in principle, you might want to actually think about about grading rather than monodromy.
Yeah.
So, in case you have two identical particles, you have to think about that. So in principle, you might run into some trouble. We basically just put some necessary conditions here, and it turns out that it always works. But in principle, you could imagine something could go wrong, but I don't know why it doesn't happen.
okay?
Okay, so then we look at the particles which aren't confined, which are just the 4 particles with quantum dimension 1, some of the Union theory, and we look at their spins, which are the 0, 0, 0, and 1/2, and with their fusion, which is basically it's a Z2 times Z2, all these things just fused to the identity. And then there's really only one theory which does that, which is the Z2 toward code, or Z2 discrete gauge theory. So if you look at these 4 numbers and these 4 numbers, you can very quickly match up the particles. Okay, so that means in this case this final theory uses the double Z2, and we have a transition between Ising times Ising star and the double Z2. And you could really imagine that transition like this would happen in 11 when lattice model, where you introduce some large perturbation in easing times easing star model, and then you end up with a double C2. Okay, so then another thing is, of course, you can have phase-separated examples like here, where you have easing times easing here, and then here you've changed the couplings of the theory. There's a double C2, and then the broken theory at the level of T, which was just easing times C2, should actually describe the boundary here, right? Because it's supposed to describe the excitations which live here but which pull strings, so they actually want to be driven to the boundary to shorten their strings. Okay, and I have a little exercise here, but you can also look this up in my big paper with Sander, that if you actually condense the other boson in this theory, sigma, sigma, then phase 2, the condensed phase, is completely topologically trivial, so you don't have any non-trivial topological sectors in it. And I'll refer back to that, hopefully, if I get that far.
Okay, can I ask another question? So if I start with 11.1 model, is there some obvious perturbation that I can put in to force this particle to condense? I mean, is there some sort of hot?
I'd say there's no obvious perturbation, but I'd like to think about. Try to think about this for a bit, and I didn't come up with anything obvious. But there should be something. Yeah. It has to make the mass of the epsilon particle go through 0 or something like that. That would be the obvious place to think. Okay. So that gave you sort of an example and sort of a general idea. So then, can we actually say anything in general about what kind of transitions we can describe by this process? So just to remind you that these quantities C and D, which characterize topological phases. So C would be the topological central charge, which is just, if you like, from field theory density central charge modulo 8. And D, the total quantum dimension, which tells you basically something about, it's the sum of the squares of the quantum dimensions of the individual particles, the square root of that. And it has to do with the topological entanglement entropy in the system with this order. And just repeat the names of the various levels of our description. And then it turns out that if you start out with a theory which is modular, which is fairly minor restriction, it's just a theory where the braiding is non-degenerate, so we don't have any particles that are invisible to other particles, to all the other particles, by braiding. Then turns out, first of all, that the central charge of the theory is conserved under these kind of transitions. That's not so surprising because you're condensing a boson, so it's basically condensing something that's not chiral. And so you kind of expect naively that central charge is conserved, but it's something that you can just observe if you look at many transitions, many examples. And secondly, there's an interesting identity between the total quantum dimensions of such theories. Turns out that at each level you can define the total quantum dimension by the usual formula. So even at the level of T, because you don't need actual grading for this. And then you have this funny thing that if you go from A to T, to the broken but not confined, not unconfined level, then you have some factor in the quantum dimensions. And then if you go from T to U, you have another factor in the quantum dimension. It always goes down, and these factors are the same. So, and you really need modularity for that. Actually. So, or in other words, the square of the dimension of T is the dimension of A times the dimension of U. And that should mean something about entanglement entropy, and I'll just a short sketch on the next slide. And the nice thing I would like to say is that actually if you have enough mathematical equipment, then there's a mathematical context where you can actually prove results like this and some other results as well. You can first of all construct T as a tensor category and construct U as a graded tensor category. You don't have to rely on silly little calculations like I did earlier in the talk, and it's all guaranteed to work. And these identities hold. On the other hand, it's not so easy to show that this mathematics really fits onto the physical intuition that I put in here. So, about this topological entanglement entropy, I'll have to go through this quickly. So basically, the topological entanglement entropy that's associated with the region that's a disk is basically the logarithm of the quantum dimension of the theory that describes the medium. So if we have a medium that has an A theory on the left and a U theory on the right, and the boundary described by T, then if we, let's say it's a sphere, if we divide this sphere into two regions, where one of the regions are these two gray caps, and the other region is the annulus in the middle. Then we have two ways of calculating the entanglement entropy, because we can either work from the caps or we can work from the inside. If we work from the caps, then we know what happens, because here this cap is perfectly inside this region with order A, so we should get topological contribution log dA. And here we should get topological contribution log du, because that cap is completely in the region with entanglement entropy described by u. So get log dA equals log du. On the other hand, this annular region is supposed to be, well, if you shrink it, then it only contains the boundary, and then you might naively expect that it's described by T, despite the fact that that's only a tensor category, not a modular tensor category. But anyway, if it was described by T, then for annular regions, because they have two boundaries, we actually should get twice the log of the total quantum dimension. So this is actually a rather unfounded speculation that we should get twice the log of the total quantum dimension. But actually it works precisely because of the identity that we had on the previous slide, which is a dt squared equals dA times u. So take the logarithm of that and you get precisely what it says there. These two things are equal to each other. Okay, so now the other thing, so that was the nice thing you can do with the relation between the d's, but the relation between the c's is actually a bit of a pain, because it means you can only describe a very restricted set of transitions in this way. So we'd like to be able to describe transitions between theories of different central charge. So a simple idea that you can apply to do this is, how can we change the central charge of a theory? We can just say, well, here we have theory in phase 1, a central charge C1. Let's just make a second layer in phase 3, and which has central charge C3, and then the central charges will just add up. Okay, so fine. But of course, in the middle here, we'll be describing the system by the tensor product of those two theories. So we really be a two-layer theory. So that's no good if we want to just describe a transition between some phase and some other phase, which isn't that phase plus a layer. But of course, you could have a two-layer system where in the two-layer part here, there is one of these topological phase transitions. So there's actually a condensate forming, so that now it's no longer manifestly a two-layer theory, but the central charge is conserved, because we know the central charge is conserved under these things. So that gives us a way of actually describing, or hoping to describe, topological phase transitions in a two-step process. First we add an auxiliary layer, which just brings the central charge from the one theory to the central charge of the other theory, just adds a difference in central charge. And then we have to do both condensation, and hopefully we'll get the right theory on the two-layer side. And the question is, are there any actual systems where this kind of process really describes two phases, and does the boundary theory mean anything in this case? Okay, so for example, suppose that we want to describe a transition between the Ising model and the Tor code, two phases with those kind of orders. So this such a transition, of course, happens in the Kitai hexagon wall. So it's an interesting example for that already. Okay, so we know that we can get the Tor code by just taking Ising times Ising star and condensing this boson, because that's what I spent a lot of time talking about just now. So what we could do is we start with phase 1, picture on the previous slide. Just take the Ising wall here. That's charge, central charge 1/2. We want the Tor code here, or here rather, which has central charge 0. So we put a c equals -1/2 here, which can only be the Ising star theory, if you want the unitary theory. So we get Ising times Ising star here, and then indeed by forming a condensate we can get Tor code here, so we get transition between Ising and Tor code there. The branching still up here from that condensation and the Ising times Ising star part. Now there's another thing that's interesting to note about this whole construction is that, okay, we actually have a natural way of labeling all the sectors by sectors of T. And when I say all the sectors, I mean all the sectors in all the parts of the diagram. So, well, of course the sectors in phase 2, which is the part where the condensate has happened, are the non-confined sectors of T. So those are just the dimension 1 particles here. But the sectors in the original theory were, of course, where you have the single layer, that's the Ising. Well, they should come in principle from the ones where I have either, where I have a 1 on the right hand side, right? So like a 1, 1, or epsilon 1, or sigma 1. But if you look at those, see all of those actually branch to a unique particle on the right hand side. So they're also labeled by a unique T label. And similarly, if I want to think about the other layer, if I want to think about a region where the other layer is on its own, I can do the same thing. So then in that case I look at the things which are trivial on the left hand side. So 1, 1, 1 epsilon, and 1 sigma. And again, this all runs to unique to unique T particle. And this is actually a generic thing. So you can show that if the theories, the layers that you start with don't have bosons by themselves, but only bosons occur because you put the layers together, then all the sectors in all the 3 phases and on the boundary are labeled by sectors of T, or the T theory. So once you know that, then you can actually start making statements about which processes can occur at the boundary, similarly to what Karel Jan Schoutens was talking about last week. So for example, if you look at this fermion 1, epsilon, so this is this can actually pass through all the boundaries. So what does that mean? Well, it's a non-confined, it corresponds to a non-confined particle, so it can occur in the condensed phase. It can also occur on the left, because of course it's identified with this epsilon, 1, perhaps it's do the same thing. And it can also occur in the top layer, so it can occur in all layers. So in principle you can think of one of these types of particles going through a boundary or through each of the boundaries without leaving any topological trace. Now, of course, the gap might go to 0 on the boundary and could be all kinds of excitations excited in this way, but there wouldn't have to be a topological trace. So on the other hand, if you look at, for example, the particle 1, sigma, let's see, that's this one. And this one is one of the confined particles, so it's actually expelled from the inner region, from the condensed region, right? So pushed to the boundary. But because it's of the form 1, sigma, it could actually just go on in the region where there's only one layer, meaning the top layer or the right layer. So it's able to pass into from the condensed region into region 3, but it can't actually pass into region 1 because it doesn't correspond to any particle on this side where it's trivial on the left hand side, on the right hand side. Sorry. Now sigma 1 has an opposite similar property. And finally, you can have interesting splittings if particles hit the boundaries. You can use diffusion rules of T. So for example, if you look at this particle sigma 1, this could be coming in from the system where you only have the left or the bottom layer. And when it reaches the boundary, then one of the fusion rules of T, or two of the fusion rules of T, are that you can split in these two ways. Which means that this one sigma is of course a confined particle, but these two particles are non-confined. So these two particles could pass into the interior, either of these, but only at the cost of leaving one of these confined particles on the boundary. So you have a topological trace on the boundary of pushing this particle through.
Can I ask you, when you translate from this more abstract language to what you are saying and being stuck at the boundaries, there is an underlying physical assumption that it's a string tension or something.
Yeah.
Right.
Yeah, this is true, yeah.
So you have to add some dynamics to say those words.
Yeah. No, that's, yeah. There is an underlying assumption. But it seems like a reasonable assumption because if you've introduced a condensate and you destroy it somewhere locally, then it should cost a certain amount of energy if the phase is gapped in the first place. Yeah.
But it's something that goes beyond the topological.
Yeah, sure. Yeah. Okay, so now I have very little time to say anything about question quantum Hall wave functions, but I'm going to try and say something anyway, and hopefully it's a very knowledgeable audience anyway. So first of all, what is the fractional quantum Hall hierarchy recipe? Well, we've seen lots of talks on this here already, so basically the idea is you have some fractional quantum Hall trial wave function, and you start with that. You have n0 electrons in position Ci, and now you want to, for example, make a state at a different filling fraction starting from there. For example, lower the density to make the filling fraction go down. So how can you do that? Well, you add some number n1 of quasi-holes at positions ui, and then you project these onto their own wave function psi, where it's important that the psi keeps the statistics of these quasi-particles. Okay, and then of course you have to integrate out over all the positions of the quasi-particles so that you end up with a wave function for just the electrons again. And finally, of course, you can add actual real quasi-holes which are really sitting somewhere at position wi, and those could have an effect in both of the layers, so in the original electron wave function or also in the wave function psi. And then you can iterate this to make as many layers as you want, but let's do one layer here, because I'm going to get any further than that anyway. So, so the wave function at layer k would be the wave function at layer k minus 1, which depends on the electron coordinates, the coordinates of the particles which are going to be integrated out, and the actual quasi-holes or quasi-particle coordinates, and then we integrate against this pseudo wave function, which depends on the coordinates that are integrated out, and again on the coordinates of the actual quasi-particles. And of course, the idea is now that there should be some way of thinking about the condensation of the particles that are being integrated out. But the question is how to do this correctly. First of all, so this has been very successful in the quantum Hall effect. You can do this with wave functions only of Laughlin type and or Jastrow form, then you get the Helling-Halpern hierarchy, which describes basically the whole first Landau level. You can, for example, do this the way that Parsa and I did it, and build a hierarchy on the Moride-Pfaffian, where the hierarchy is again, all the pseudo wave functions are of Jastrow type, and you can do various generalizations, which have also been talked about here. So, for example, Levin and Halpern generalization, or Marias, Hermann circle generalization. Anyway, the claim or hope that I would like to stake here is that, well, at least if you want to just look at the topological order of these hierarchy states and look at domain walls between them, then you should be able to describe that by post-condensation in these layered systems like we was describing in this talk up to now. So how does this work? Actually, it's not a very deep application of this whole framework, but it's nice that it connects to physics. So why I want to show you. Okay, let's look at the filling 2/7 abelian hierarchy state. So how is that built? You start with the nucleus 1/3 Laplace state for the electrons, and you make some quasiparticles. The quasiparticles have their own statistics, and then you put the quasiparticles in some pseudo wave function, which has the same statistics, and you conjugate that pseudo wave function, and you integrate over the coordinates of the quasiparticles. And of course, there might be more actual real quasiparticles which are really sitting somewhere, which I put in the quasiparticle gas only in this case, so not in the electron wave function. Okay, so well, how are we going to describe the topological order of this thing? Well, before we do the integration, it looks like we're writing a two-layer state. In the first layer we have electrons, which basically well, we have particles, the quasiparticles, the smallest ones, which basically carry a Z6 quantum number, because the smallest charge is 1/3, and it doesn't become topologically trivial until we reach 2 electrons, because an electron is still a fermion, and that's not trivial. That's 6 times 1/3, so basically we can describe the fusion in that theory by Z6. And we also know the spins. They're basically L squared over 6, where L equals 1, 0, 1, 2, 3, 4, 5. Okay, so in the second layer, because we needed to make this wave function here have a, well, 1/3 plus some integer, to make it have the same statistics as here, for we use, we end up with 7/3. But then if we want to make some quasiparticles, we get 3/7. And if you think about this a little bit, then you see that the conformal field theory describes this thing, as this square, as basically these operators creating the particles. So basically, it's a Z0 42, the second layer. So we have a Z6 times Z0 42, and I put a star on Z0 42 just because, well, the weights are going to come with negative signs, or there are stars on the coordinates, how you like it. So then, the thing we want to do is we want to actually identify the quasi-hole in layer 1, which is 1,0 in this theory, with the electron in layer 2. So that's actually the 0, -7. And then we want to assume that this thing condenses. Okay, so if you assume that the 1,7 forms a condensate, then what happens, of course, is that in the first step of our framework, we see that 0, 0 becomes identified with 1,7, 2, 14, etc. And then, of course, for 0, 1 and 0, 2, we get more of these orbits. So we actually end up with T sectors, which just correspond to 0, 1, 0, 0, 0, 1, 0, 2, etc. to 0, 42. And of course, they have the obvious fusion as well, so we end up with just a Z42, which is our T theory. Okay. And then if we look at confinement, we have to require that if we look at two of these things, and we look at where they come from in the original theory, they have the same spins if they're not confined. So basically that's expressed by this formula here. And it turns out then that you're only left with the particles where these labels in Z42 are multiples of 3. So actually you end up with Z14. But this is what you expect, because in this theory, the 2/7 state, you have of course E over 7 excitations, and you have to make 14 of them before you get the 2 electrons. And then, so the topological order should be described by Z14. Okay. And you can of course calculate the spins and the charges, etc. for these particles, and it corresponds to what the usual way of doing things is. Okay, let's see. So can you do actually any physics with this? Well, Karl-Jan Schoutes also showed a similar idea to this. So, well, of course you can do some physics with this if you want. You can think of a situation where you have a quantum dot at one filling fraction. In this case I took 1/3 and 2/5, but the whole situation is basically the same. You end up with a Z15 instead of a Z30 instead of a Z42. for the boundary theory. You have a quantum dot of nu equals 2/5 sitting inside a sea of nu equals 1/3. And you have a tunneling current which flows at this contact here at T2. There might be some other contacts, but we can just ignore them. This tunneling current should be influenced by the proximity of this dot. So, if you put more charge on this dot, this current will, notice the effect. So, as you actually put some flux through this dot, what happens is that because this dot is at nu equals 2/5, you're trying to push out a charge of 2/5 E. But you can't push all of that out because in the outside region you only have E/3 charges available. So what has to happen is that if you push this out, a 1/15 charge gets stuck on the boundary here, in the same way that we were talking about, and the E/3 gets tunneled out to the outer boundary. But that means if you keep charging the dot in this way, then you start off with extra charge 0, then extra charge 1/15, then 2/15, then 3/15, etc. Until you reach 5/15. And then you have 1/3 again that can tunnel out, so you're back in the original situation. So naively what you expect is that as you put more flux through this dot, the period of the behavior of this point contact is 5, and then in 5 flux contact. Of course I didn't think of this myself, so this is actually from a paper by Fikofal and Fisher. I just applied our whole scheme to it. They actually say that this could explain the experiments of Goldman et al. And they basically say that they have this picture, and they say the sample could be contacted like the samples of Camino Goldman et al. So you can draw conclusions for yourself what they think of Goldman's experimental capacities. But anyway, it does get the right periodicity. I'll finish up very soon. So for the hierarchy on the Pfaffian, you can basically do the same thing. So if we look at the Pfaffian state, we have the Pfaffian state here for the electrons, and then we make E/2 quasiparticles, which are basically just the Laughlin quasiparticles, and they have their own statistics. And then they have their own pseudo-wave function, and you can introduce some quasiparticles, which are just in the second layer, so they're just abelian quasicles, like in the previous example. This is this 12th state that Barca has given a talk about to propose. Except now you have an interesting new thing, which is that you can also make non-abelian quasiparticles, because, if you write this whole first bit in terms of conformal field theory, then of course this Pfaffian with the Zi and Cj squared is just a correlator of these electron operators here. Then the E/2 quasiparticles are created by these operators. But now we also put some E/4 quasiparticles in the first layer. Okay, great. Then we make the pseudo-wave function for the E/2 particles. And now it turns out that in order to make the E/2 quasiparticles local with the E/8 quasiparticles, when we condense them, we have to introduce this factor here with the 1/4 between the so basically we have to introduce this thing here, and as a result the whole thing is local. It's not an actual, it gets rid of the branch path. And then if you want to look at, okay, well, so what type of abelian conformal field theory is creating this stuff here, then you immediately see that you have to have a 1/40 here, and that is actually a Z-mod 40. So you end up with the Ising times Z8 and restricted to the even sector, which is basically just the theory that describes the spectrum infusion of the 5-half state, the Pfaffian, times the Z40, the start. And of course, you can again write the vertex operators for the two U1 factors. And now again you can condense, like I said before, so you condense the particles, which corresponds to the E over 2 quasi-particle, and then you end up with basically two classes of sectors. You have either 1 or psi 0, p, or sigma 1, sigma, 1, p. It's all the same as before. P and Z40, you have 120 sectors in T, and after you do confinement, then you reduce by another factor of 4, and then you have 30 particles, and the whole thing looks, again, just like an easy model with some extra ambient charge. Okay, so I'll skip that example, so I don't talk about that in detail. So in conclusion, so what we've done is we've extended this topological symmetry breaking scheme to deal with transitions that change the central charge and where you can think about domains. And we show that the PS and Halperin hierarchies fit into this framework. So, of course, we didn't do any microscopics, so it's kind of like doing transitions without looking inside the box. So that has its good and its bad sides. Good side is that it makes things a lot less technically difficult. The bad side is that you have to worry that maybe you're missing something important. Well, the good thing about this is because it seems so independent of microscopics, it also seems that it fits onto a lot of other recent developments, at least to some extent. So, I already mentioned Grosvat and Schouten's construction for Nelson Reed, which is also in some way duplicated or similarly produced in the anionic lattice models of Grills and Erdőn and Trips, etc. And also the simplest case of Maria Hermann's hierarchy looks kind of similar to that. There's also these 11 Halperin hierarchy states where if you look at our whole state, it's like having a leading times leading star with the sigma-sigma type condensate. So I already said that kills off all the non-leading order, and that is sort of explains why they have only abelian topological order at the end. And yeah, so let me end there.
Questions? So, the boundary theory, is T, the central charge of that is always the one of the two copies, or I got confused here?
Oh yeah, the T, it's kind of a problem to think about.
Because in your abelian case you have +1 minus 1, you would get 0, the boundary, you just take the central charge. You do the Z theory, U1 times U1 star, you get 0, or you still have the
Oh yeah, I see what you mean. Yeah.
So I got confused there.
Yeah,
You expect to have a U1 left somehow, or not?
Yeah, no, I
Not
understand. You expect to have a U1 squared, right? Yeah. Because of the bar, it looks like I'm subtracting the kind of terms. Yeah. That's a good question. I need to think about that. So it could just be a matter of having the
Well,
Yeah.
probably it's just
Yeah.
removing the bar and then
and then
gapping out one node and you're left with one or
Yeah.
something like
I
that.
need to think about that a little bit. But in general, it's kind of difficult to think about the T theory as a conformal field theory, usually not exactly a conformal field theory. Which is also not that surprising because, well, you know, if you were going to just look at one sample where you go all the way down and you don't have an interface, but you just have an interface with vacuum, then you'd expect that the conformal field theory, which occurs on the boundary, is just has one, according to holographic principle, has one particle for each of the point-like particles inside, so for each of the U sectors. But you still expect that you have different boundary conditions for each of the T sectors somehow. So it's kind of not trivial to untangle the conformal field theory out of the T theory.
In some of the examples you mentioned, you do get it naturally.
Yeah.
Is there, I mean, this, the example you gave, the Ising example, Ising cross Ising, you end up with two sigma-sigma particles.
Right.
And is that number 2 somehow related to the fact that there's two fusion channels with the sigma that you started with?
Yeah, it's related. So, well, at which level is kind of difficult. I mean, in the end, of course, the reason that this thing has quantum dimension 2 is because the sigma has two fusion channels and it has quantum dimension square root 2. And if you take two of those things, you get to quantum dimension 2. But but you obviously probably would like to say something like, oh yes, but if we think about these two sigmas and they fuse in one channel, then that's the sigma one. But you can't really think that way. Yeah.
Can you connect this in simple cases to Chern-Simons theories where you can actually think of condensations and
Yes,
having an actual expectation value of no parameter heat?
Yeah, I think you can, because for example, if you take an SU2 level 4 theory, then that has a boson, which is the highest representation of the SU2 level 4. So in principle, you should be able to try to condense that in the Chern-Simons theory. Of course, the problem with that is that you don't really have a field to create those things in the Chern-Simons theory, because they're described by Wilson lines. So you have to introduce a field that creates Wilson lines. But
Maybe we should go to a matter.
Yeah. So I think it is possible to think about that. Yeah.
Because it's this whole hierarchy construction by Chang and Peterson and Lee and etc. Question is to what extent that expresses this and whether it can be extended.
Okay. Yeah,
I mean, to your hierarchical states, for instance.
Yeah, it certainly will be interesting to try and find out. Yeah. I don't necessarily know the answer, but
So I know from your paper that you can get any coset by doing the symmetry breaking.
right.
But I mean, can you get to any, Drinfeld double by? I mean, is there some way to get to? If I start with some simple theory and symmetry break it, can I? Is there some? I don't know.
So it's not necessarily clear that you can just get to any Drinfeld double that you want. It's if you work with Drinfeld doubles, like one thing you can always do is, okay, you can, but it's kind of cheating. So you can start with the Drinfeld double, for example, some larger group, and then you can just break the symmetry in such a way that you go down to the Drinfeld double of some smaller group, and then you say, oh yeah, I produced that one.
So the fact that you got Ising, from Ising across Ising star, and you get down to toric code.
Yeah.
That's rather.
Yeah, that's kind of mysterious and interesting.
Yeah, that sort of suggests that maybe generally you can get.
Yeah, it's an interesting conjecture. But I don't know. Certainly it would be nice if that was true. So maybe if you start from arbitrarily large Lie groups and double them, and then you could get like arbitrary subgroups of finite subgroups of that Lie group or something.
Right.
Well, for SU2 that already doesn't work. So at that level anyway. Yeah. But it's certainly again interesting.